The pandemic has accelerated the introduction of technology in all aspects of society, but, especially in the semiconductors industry, new technology moves fast, whether there is a pandemic or not. For example, 2 years ago, IBM was a Semicon West, a traditional gathering for the semiconductors industry, and one of the keynotes was delivered by IBM Executive Vice President John E. Kelly III. Kelly talked about some of the experiments of quantum computing that were at the very early stage and were conducted at the IBM Watson Research Labs. More recently, at Semicon 2020, which took place in virtual format, John Kelly was again a keynote speaker, but this time he could mention real, commercial applications of quantum computing. Quantum computing, in fact, is a new exponential, a sort of new Moore's law for the semiconductor industry.
Exponentials are more common than we can imagine, and the impact can generate universal problems or global opportunities. We invite you to watch a video about exponentials from the same event, which tells exactly how exponentials work. The main message is that the technologies that have driven the growth of semiconductors in the last 50 years, and that have affected every aspect of our life, cannot address the grand challenges, like weather forecast, health, water shortage, finance engineering, or discovery of new materials.
There are just too many grand challenges facing us as a society and as humans, and too many opportunities. Whether it's taking man now to Mars and beyond, whether it's solving the challenges of an education system, particularly during a pandemic, global climate change, which is affecting much of the earth, secure food supply, fires, or challenges in healthcare. These are all things that can, in my opinion, only be solved with technology. So what are some of the breakthrough technologies that are required for these grand challenges? Well, you saw it's all about data and getting that data to where we can use it. And as I said when I was last with you, presenting a few years ago, artificial intelligence is the way forward. AI is, in a sense, analytics on steroids. Many new devices will be required to really drive artificial intelligence at the scale of the kinds of problems I just showed you. The second set of grand challenges in technology revolve around not just cloud, but edge computing and cloud at the edge. The data will be generated in enormous amounts at the edge, and that's where we will need to store the data and compute on the data in software-defined clouds. And lastly, and very importantly, is quantum computing. We just do not have, nor can we create with classical computing, enough computing power to really look at some of the biggest challenges that we have. So let me speak about each of these key technologies. Artificial intelligence devices. Clearly, with the amount of data, we can no longer use just simple von Neumann architecture and move the data to the compute and back and forth continuously. We frankly have to do the compute inside the memory. So new kinds of devices and new kinds of structures are required. Deep neural networks, the backbone of much of today's artificial intelligence, will have to be mapped into new kinds of devices. And many of those new kinds of devices, particularly in non-volatile memory, will require new materials. We're going to have to use most of the periodic table. Edge computing and cloud, just a few examples. Think about trying to do diagnosis of skin cancer remotely. It takes enormous compute power and a lot of data, but it can be done. We can detect edges and shapes of melanoma on skin and determine whether you need to see a doctor or not. We can verify through things like blockchain at the edge whether entities are real or not. And as I showed you, we can create enormous remote networks, even on some of the most remote lakes in upstate New York, to collect data and analyze data on the spot. And lastly, quantum. Now, I think one clear way to look at this, and simple way, is there's a whole bunch of problems that we can solve with classical computing, with our bit switches. And we've been doing that and will continue to do that for decades into the future. But there are many problems that are just too large or, frankly, exponentially grow as we try to scale the problem. And therefore, we need a new kind of computer, a computer that operates at the quantum scale. Problems like chemistry, modeling even simple molecules like methane at the atomic level and all of the vibrational states is frankly impossible on a classical computer. We have to make countless approximations to try to do it. It can be done in real time at great precision on a quantum computer. Or think about modeling the financial systems of the planet. Enormous, complex, interrelated problems. Optimization can be done on a quantum computer. And frankly, even things like supply chain, which you think might be simple, because of the number of variables and permutations, again, we run out of classical compute power. They can be optimized and run on a quantum system. Now, let me give you an update on where we are on quantum computing. When I was last with you, again, a few years ago, we were in advanced development at IBM, right here in Yorktown Heights, in quantum systems. And we had working qubits, and we were making progress, and I said, watch this technology. It's going to move fast. Well, it has. We went from that lab system to a commercially available system on our cloud in the past 2 years. And in fact, when we look at the progress being made in the quantum volume, which is the ability to add good qubits and have them compute, we have been on a new exponential. That's right, a new exponential. We're doubling the quantum volume every 12 months. Sound familiar? Moore's law for quantum computing. Great advances. And when we extrapolate in just a few years on that line, that exponential, we're going to be able to solve many of the problems that I showed you in the last chart. So let me wrap up. When I reflect back and I listen to people around the world talk about our semiconductor industry, over the years I've heard time and time again, well, we're going to be able to go another 1 or 2 nodes and then we won't be able to go farther than that. Or I hear, well, this is getting to become a Rust Belt technology industry. I can't understand how people can say that after 50 years of advance. And frankly, we're not any place near the end. In fact, as I think the great Winston Churchill said, technology is advancing very quickly, and we're not at the beginning of the end. We're at the end of the beginning, and the best is yet to come. And all of this is going to be driven, again, by extreme innovation and extreme collaboration. And in IBM, and for me personally, it's a privilege to know all of you and work with you as we advance these technologies and solve the world's grand challenges.